Hi everyone, my name is Hamed Gorjiara from UC Irvine. Today I'm going to talk about our system, Yashme, which is designed to automatically detect a new class of persistency bugs that we call it persistency race. This is a joint work with my advisor and co-advisor Brian Demsky from UC Irvine and Harry Zhu from UCLA. Persistent memory is a new technology which provides byte addressable access to persistent data through normal CPU load and store instructions. This new memory provides higher capacity with only 2 to 3 times higher latency compared to traditional DRAM. In using persistent memory, the program needs to guarantee crash consistency. This is challenging because there is a volatile cache between CPU and persistent memory that delays the persistency of store instructions. Therefore, a system crash can cause either data not becoming persistent or the persistency order to be different from the program order. There have been a lot of testing frameworks implemented to identify such persistency bugs in the programs. We present a new class of persistent memory bugs that we call a persistency race, which arises because of the interaction between compiler optimizations and persistent memory. Most programming languages specifications, including C and C++ memory models, provide compilers with the freedom to assume that the programs are race-free and other threads will not read from a non-atomic store until a release operation such as unlock is executed. This race freedom assumption allows compilers to perform different optimizations on non-atomic variables, leading to splitting them into multiple store instructions, which also known as store tearing, or generate new store instructions to temporarily stash intermediate results in the memory location if the compiler runs out of registers, which this is referred to as store inventing. So the compiler only needs to guarantee that the optimized code does not store to any memory location that the original code did not. And a store takes full effect before the next release operation, such as unlock or store release. However, with persistent memory, system crashes can result in such temporary values become persistent. To illustrate the idea, let's look at this piece of code where the program writes the hexadecimal value of quadruple f's to variable x and then flushes this variable. As you can see on this slide, x initially contains hexadecimal value of quadruple a's in the memory. Variable x is non-atomic. Therefore, the compiler can freely decide to split this store into multiple store instructions x1 and x2. When the program is running, CPU executes store x1 first, and the corresponding cache line is updated. If there isn't enough space in the cache writes back dirty cache lines to the memory. Consequently, x1 possibly can become persistent. In this state, if the system crashes, x2 store is lost since CPU registers and the content of cache are volatile. In the post-crash execution, when the program reads from variable x, it observes an invalid partially persisted value of double F double A. Variable x can be a pointer where this invalid value may lead to a program crash due to illegal memory access. We refer to this bug as persistency race, since a pre-crash execution thread races with the crash, and the post-crash thread observes the effects of the race. In general, standard compiler optimizations can potentially lead to persistency races. For example, in the piece of code on the left, x is a 64-bit integer that the pre-crash execution writes a value to it and then flushes x. The post-crash execution simply reads from variable x. If we compile this program with GCC compiler with O1 optimization level under ARM64 architecture, a single write is split into 6 assembly instructions, and consequently, a poorly timed crash can cause to read a partially persistent value for x. Although it is rare that compilers introduce these optimizations, it is enough of a concern that both PMDK and Linux kernel developers take care to avoid it. Another case of persistency race is a common optimization by both LLVM and C++ for both ARM and x86 platforms, where the compilers replace a sequence of assignments to contiguous fields with libc memory functions such as memset, memcpy, and memmove. These functions do not guarantee 64-bit atomicity, and consequently, this set of optimization may result in store tearing, leading to persistency races. We investigated the source code and the generated binary for CCEH and FASFER and 4 benchmarks of recipe, and we realized that there are 27, 2, and 22 cases where a normal write in the source code is replaced by the memory operation in the binary. This study shows this optimization is actually very common in practice. Although the store tearing could be prevented at low cost by changing the specification of these operations, however, these operations are part of the C++ standards, and it's not trivial to change the standard specifications. It's a time-consuming task, and at the end, it is possible that the standard writers decide not to change it since the language is already providing a correct way to avoid it, which would be using atomics. We designed and implemented a new tool called Yashme to detect persistency races in the program. Yashme is the first tool that can identify this new class of persistency bugs. Yashme is implemented on top of Jaru, which is a model checking engine to run programs and simulate crashes in them. To use Yashme, the program has to be compiled with LLVM frontend, which instruments all memory accesses, cache, and fence instructions in the program. Then, after executing the binary file, Yashme controls Jaru's scheduler and picks an interleaving and a target crash point. Then, the runtime systems runs the program and simulates the target crash and reruns the program to recover from it. Yashme monitors both pre-crash and post-crash executions to compute which stores may be partially persistent. This process repeats until there are no more new executions in the model checking mode or reach the maximum execution limit in the random mode. At the end, Yashme reports all persistency races found in the program. To demonstrate Yashme's basic approach, let's look at the following example to see how Yashme ensures that stores are fully persistent. On the left, the pre-crash execution writes to X and then flushes that variable. Then it writes to an atomic variable Z, and the program crashes before flushing this variable. X and Z are initialized to 0 at the beginning, and they are located on different cache lines. The post-crash execution first loads value of 2 for C, and then it reads from variable X. For this example, since the pre-crash execution explicitly flushes the cache line after the store, and the flush happens before the crash event, the store is fully persisted, and the post-crash execution will read the hexadecimal value of quadruple A's for X. In addition to flush operations, Yashme relies on cache coherency to ensure a total order in the persistency of the stores to the same cache line. To illustrate the idea, let's look at another example. On the left, the pre-crash execution stores value of quadruple F's to X and writes 20 in variable Y, and then the program crashes. In this example, we assume X and Y are located in the same cache line where Y is atomic and X is a non-atomic variable initialized to quadruple A's. The post-crash execution reads value 20 for Y. Since X and Y are on the same cache line, cache coherency guarantees that store to X, the first instruction, is completely returned to the cache line before the store to Y, even if a store to X is torn into multiple stores. Since the post-crash execution observes the store to Y, the cache line is flushed sometime after instruction 2. In other words, since the post-crash execution reads from a later atomic store to the same cache line, it also must observe the fully completed store of quadruple F's to X. The main challenge with basic approaches is that detecting persistency races require the crash to fall into a small window of execution after the store and before the implicit or explicit cache line flush. On the right, you can see the pre-crash and post-crash executions of a program, and on the left, you can see the timeline of operations executed in the pre-crash. Since the crash is simulated outside of the detection window, no partially persisted value is observed by the post-crash execution, and consequently, no persistency rates will be reported for this scenario by basic approaches. However, if the crash was simulated inside of a detection window, the post-crash execution could observe partially persistent value of double F, double A in variable X and report a persistency rate for this variable. This requirement dictates aggressively injecting crash events in the great number of executions and exhaustively exploring thread schedules. The key idea in Yashme is to expand the existing detection window to make more races observable. In other words, Yashme does not rely on perfect crash events to trigger races. Instead, given a target crash event, it derives executions that share a prefix with the pre-crash execution, up to and including all stores that the post-crash execution read from. This expansion technique enables Yashme to detect races in derived executions without the need to actually execute them. The idea is that when the pre-crash execution has flushed the store instruction, but the post-crash execution has not read from any stores after the flush, we can ignore the flush operation to find persistency races in the executions that we are not currently exploring it. To demonstrate the idea, let's take a look at an example. On the left, the pre-crash execution writes to X and flushes the variable and do an atomic write to Y, and then the program crashes. On the right, the post-crash execution reads from variable X and Y. In the middle, you can see the timeline for pre-crash operations. The red arrow shows the constraint of crash interval that is consistent with the stores read by the post-crash execution. This constraint shows the range of the places that crash could have happened. Initially, the post-crash execution did not read from any stores, so the crash interval includes all operations in the pre-crash execution, which means Yashme derives 4 executions from the pre-crash execution where the crash could have happened before instruction 1, after instruction 1, after instruction 2, and after instruction 3. By executing the post-crash code, after reading the value of quadruple A's for X, Yashme updates the crash interval where crash has happened after execution of instruction 1. Yashme infers that one of the derived executions crashed before the flush operation and does not execute the flush. Therefore, Yashme reports persistency rates on reading from variable X without actually exploring this derived execution. As the post-crash execution progresses and reads from more writes, Yashme updates the constraint for crash interval to be consistent with the post-crash execution and looks for more persistency races with the updated constraint. Fixing persistency races is very simple. The developers only need to replace problematic non-atomic stores with atomic stores, so compilers avoid performing any optimizations on them, leading the values becoming partially persistent. We evaluated Yashme on fastware, CCCH, and 4 recipe benchmarks. These benchmarks are a collection of data structures such as B plus tree and different DRAM indexes for persistent memory. In total, Yashme found 19 persistency races in these benchmarks. Here you can see one example of persistency races that Yashme found in CCEH. On the left, if the pre-crash execution could write sentinel value to the key of the given slot, then it updates its corresponding value and key with proper values. On the right, the post-crash execution looks up for a key, and if it matches with the key of any slots, it returns the corresponding value. This code suffers from persistency races since key and value aren't atomic. And a key can be partially persisted due to a poorly timed crash. This can lead to data inconsistency in the data structure, and the post-crash execution can accidentally read from a key that never be inserted to the data structure and return wrong value. In addition, we evaluated Yashme on a set of real-world frameworks such as PMDK, which is a popular library for accessing persistent memory, Redis, which is a well-known in-memory database and memory cache, and Memcache, which is a high-performance distributed memory caching system ported to use persistent memory. We found 5 persistency races in these frameworks. We reported persistency races found by Yashme to the developers of these tools to validate our results and help them produce more reliable systems. Most of these persistency races are confirmed by the developers, and the corresponding fixes are publicly available in the GitHub repository of these frameworks. For each of these benchmarks, we compared the execution time of Yashme with Jaru, the underlying infrastructure. In this figure, the y-axis represents time in seconds, and x-axis shows the names of the benchmarks. The blue bar represents the execution time of Jaru, and the red bar shows the execution time of Yashme. As it can be seen, Jaru and Yashme have comparable running times because the race checks introduce minimal overheads. To conclude, testing a persistent memory program is very challenging, and compiler optimizations add even more complexities. As a solution, we presented Yashme, the first tool to detect a new class of persistency bugs, which we call a persistency race. Yashme uses a novel approach to find persistency races in executions without actually exploring them. We evaluated Yashme on real-world frameworks and a collection of data structure, and it found 24 persistency races in these frameworks with negligible overhead. Yashme is open source, and it is publicly available at the link provided in this slide. Thank you for listening to my talk.